The previous unit that we were working on was electrostatics, and so there we looked at charges, we looked at the interaction between charges, and we saw that between charges there are forces. It could be force of attraction between opposite charges, force of repulsion between like charges. There's also electric fields that happen around charges. It could also happen between plates. We looked at what happens when a charge goes in an electric field and how a positive charge will fall along the field lines and a negative charge goes in the opposite way. And so now, instead of looking at just one charge, we're going to look at many charges and what happens when many charges are moving along the line. More specifically, how it creates a current. And so this unit is on circuits, or specifically DC circuits. The other type of circuits is AC circuits, which is what you would get from plugging something into a wall outlet. But with those circuits, they're a bit more complicated because they come from a generator and it's an alternating current, hence the AC. And so DC circuits, it's a lot more straightforward, and it's more towards what we need to know in grade 12. So the first part that we look at when we handle circuits is we're going to start with a cell. And a cell is what provides the energy for a circuit, or the current. And so this current can be something like this. This is a very basic view of a cell. So imagine a beaker with two different types of metals in it. And one metal is a material that gives up electrons easily, and the other one is one metal that grabs electrons easier. And between it, you have you have an electrolyte. Now this electrolyte grabs the excess electrons and pulls them over here. And so it's grabbing electrons and so the excess electrons are built here on the negative side. Now this will continue until the metals break down, or the electrolyte breaks down, and then at that point your battery or your cell isn't very good anymore. And so what's done is we connect this to, I don't know, a light bulb. And then once we complete the circuit, we allow the flow of electrons to go through, powers the light bulb, and continues on. So once the electrons make it here, it gets pulled back and off it goes. Now the way a cell is drawn, and we'll be using schematic diagrams or circuit diagrams, we draw a cell like this, where the long side will tend to be the long side is a positive side and the short side is a negative side, and that represents a cell. Now what we will use in circuits are batteries. Batteries are made up of cells. It could be one cell, and normally a picture of a cell represents 1.5 volts, or it could be multiple cells, and so on. So something like that would represent 4.5 volts. However, there is a limit. If there's a 35 volt battery or something like that, we're not going to draw all the cells. And so normally anything over 2 cells, we just draw 2 cells, and above it we write down the voltage. Now the cells will provide a current for our circuit. So the current is how many charges go by per second. And one analogy that I'll use in this unit a little bit is that of a river. They're not the same. There's some big differences between the two. But just to be able to visualize it a little bit better, if you stand by the side of the river and you imagine every drop of water going by as charges, then the more drops of water going by tends to mean that it's going by faster. The more droplets going by per second, that's a faster current. And so in this case, the more charges going by per second, that will be a greater current. Now the current, we use amps. It's measured in amperes, and the symbol would be something like amps. So we would say 5 amps, 5 amperes. So if we look at a couple examples here, we have how much charge passes a point in a wire every second. And so if we have a 3 amp wire, that's the same as 3 coulombs per second. And so if we multiply this times 60 seconds, then we have 180 coulombs charge going by in 1 minute. Now if we want to see how many electrons are actually going by in a single minute, what we can do is we say the number of electrons is, we have 180 coulombs in 1 minute, and we divide this by elementary charge, 1.6. And that's the charge for every electron. And that's how many electrons you'd have going by in 1 minute. Once we connect a battery or a cell to a circuit, what we'll have is a voltage. And remembering from the last unit, voltage is the potential difference between two ends of that battery. And so that's what will provide the current for your circuit, is coming from that voltage. Now, if we apply a voltage, we'll get a current in the circuit. And that current will actually depend upon what your circuit is like. More specifically, we use Ohm's law. And what this says is we can determine the voltage of a circuit if we know the current running through the circuit and we know the resistance. And so this is our new term here, is the resistance. It's the ability to slow down electrons flowing through your circuit. Sometimes it's done intentionally, where people will put resistors in the circuit because the current is too high and will blow up your light bulb or something. Other times it just comes with your circuit, and almost everything you add to a circuit will have resistance. Resistors, of course, will have resistance. Different components of your circuit, even the wires itself will have resistance, and that the longer wire you use, the more resistance you'll have. Even the battery has something called internal resistance. So resistance is something that's added to your circuit, and the more resistance is added to your circuit, the more it slows down or reduces the current. Now this new unit here for resistance is the ohms, and we use the symbol omega. So if we take a look at an example here, then if we are trying to solve for resistance, we start with Ohm's law, V equals IR, and we rearrange it that we're solving for resistance. And so what's the resistance of this oven here? It's voltage over current, and it's 320 volts over 4.3 amps. And that gives us a resistance of 51 ohms for the oven. Now the next question is, if you accidentally plugged in the oven into a regular outlet of 110 volts, how would the current change? Well, the resistance of your oven wouldn't change, and so regardless of what you plug it into, the resistance is always the same. So now what we're going to do is we're going to take Ohm's law and rearrange it, solve it for current, and so current is going to be voltage over resistance, and now we have a voltage of 110 volts, and we divide by resistance of 51 ohms, and we get 2.2 amps of current. Just a bit of a side note, the regular amount of electricity, voltage that we get in a household is 110 to 120 volts. So by default you can say 120 volts anytime we're using something in the home. There's also a second line that comes into the house for certain appliances that need a lot of voltage, and so those will be from 220 to 240 volts. Very few things actually need it. The dryer is one that comes to mind, and your oven. They even have special outlets so that you don't accidentally plug something else into it. There are other places in the world where the regular voltage is 220 volts, but here in Canada, in North America, is generally 110 to 120 volts.